All right, let's do it. Let's talk about programming. So eventually we're going to get into C++, which is the language that we're going to learn in this class. All right, so to get there though, I have to give you a bunch of brand new terms and examples. So I'm going to show you a lot of things and that might overwhelm you. All right, please keep coming back. The more and more you try these things out yourself, especially, like try to write this code yourself once I show you how, the more you practice with it, the better you're going to get. But it's okay to feel overwhelmed during this first lecture. There's no way around it. You're going to have to see a bunch of brand new stuff. So just mentally prepare yourself right now for that, okay? So yeah, let's get started. And one thing I like to do in my classes is ask little mini exercises to have you like stop and ponder stuff. So in person, I'd be asking you to work with your peers. That's called peer instruction. But online, I'll still be giving you these exercises to just pause and try yourself, and then I'll show you my answer. So every in-class exercise in our class can be abbreviated as an ICE, and our mascot at Clovis is a bowl called the Crush, which I don't fully understand how that happened, but we're going to go with it. And so naturally that means every in-class exercise in this class is going to be called a crushed ice, which is hilarious in my mind. So yeah, I'd be asking, if this were the in-person class, I'd be asking all these questions about like, what's your major right now? How much do you know the Linux/Unix terminal? How much do you know about C++? And I expect you to probably be answering, I've never seen this stuff before. I have no clue what you're talking about. And that's fine. All right, but some of us have some knowledge, and I wanted to see that. So that's the kind of questions I'd be asking in person right now, but we're just going to keep on trucking. I'll ask some normal, like, content-based questions later for you to try, but let's get into it. Let's talk about computers and programming now. So I think that you are all already programmers. So all a program is just a recipe, all right? So if you have ever, like, looked at a recipe and followed it, you've essentially run a program. If you've ever modified a recipe or written one yourself, you have written a program, all right? So another good word is algorithm. So an algorithm is the kind of thing that makes up a program. It's just a sequence of steps that solves some problem. So it's essentially like, it's another recipe, okay? So maybe you can think of a program as just a combination of a bunch of mini recipes that are algorithms, all right, to build some final thing. So here's a silly question that I want you to think seriously about, though, okay? So how do you make a peanut butter and jelly sandwich? Please pretend that I have, like, amnesia. I have never heard of peanut butter and jelly before or something. How would you describe it? How would you describe how to make it? Please write the program to make a peanut butter and jelly sandwich for me, please. And I'll pretend that I'm a computer, and I'll run that program, and I'll make that peanut butter and jelly sandwich for you, all right? So I promise I'm going somewhere with this. But, like, what would you say? How would you write the program that says, all right, this is a program that builds a peanut butter and jelly sandwich. What is the recipe? So if you were like me when I took CSCI 40, you would say something like this. Like, all right, to make peanut butter jelly sandwich, you would get some bread, and then you'd put peanut butter on the bread, and you put jelly on the bread. And voila, you have a peanut butter and jelly sandwich after that. All right, so that's probably what you're thinking right now. And let's pretend that I'm a computer and I'm going to run your program to make the peanut butter and jelly sandwich. So you're like, all right, get the bread. And so here's my, here's my best drawing of a bag of bread. Got to be three-dimensional, right? So here are all the mini bread slices in the bag of bread. So there's my bag of bread. And let me move it over here. So like, all right, your program was, all right, get the bread and then put peanut butter on the bread. So here's the peanut butter jar. So I am the computer running your program, making peanut butter and jelly sandwich. So here is the peanut butter jar. So you're like, all right, put the peanut butter on the bread. There, I did it. I put the peanut butter jar on the bread bag. And then you said do the same for the jelly, right? So here's the jelly jar. I'm going to put that on the bread bag too. And voila, I've put peanut butter and jelly on bread, and I have made you a peanut butter and jelly sandwich, just like you wanted, right? Ta-da! Shiny and new. Obviously, that's not what you wanted, right? So this is the first interesting fact about computers that we're going to learn today. So computers are very smart. They can do a lot of cool things very fast, but they're also super dumb, all right? So you have to kind of talk down to a computer when you're programming it. You have to tell it stuff at a level that it can understand and at a level at which there is no ambiguity, all right? So there was a lot of ambiguity in the recipe that I said, right? So there's a better way, and I'll show you that way, all right? So I want you to start thinking like a computer, and the term for that is computational thinking, all right? So to do it right, we have to learn to think in terms of little bite-sized operations that the computer can perform, and learn how to break our big problems down, like making peanut butter and jelly, into those smaller pieces that are not ambiguous to the computer, all right? There's also a concept of sequentiality, like you got to do this before that, and so we'll get into that too, but that's all those things in a nutshell is called computational thinking, and that's the job for me to get you to think like by the end of this semester, all right? So a better example, a better recipe then, in terms of computational thinking, one that the computer could understand would be something like, all right, go get a plate out of like the cupboard or the drawer or whatever, and then get a knife as well, and then open up the bread bag, take out 2 slices of bread, and then put them on the plate separately. Unscrew the peanut butter jar, get some peanut butter on the knife, and spread the peanut butter onto the bread. Do the same for the jelly on a different slice of bread, and then put the 2 slices together where the peanut butter touches the jelly, because you could have done it the other way, right? And that's still wrong. So that's how you would tell a computer to make a peanut butter and jelly sandwich. That's the kind of level at which you need to think at, okay? So hopefully that makes sense, and I promise you're going to get better and better at it the more you try. So that's going to, like that way of thinking is going to give us programs that work, all right? So here's a silly meme from the internet that also exemplifies this idea of computational thinking and ambiguity, all right? So yeah, let's next talk about just like, here's some more ideas, here's some more terms that I have to throw at you before I do anything, all right? So these are things that we will cover in depth later for sure. You've already seen algorithm, right? That's just a sequence of steps to do something. That's another word for a recipe, essentially, but it's more generic. And then also testing is going to be a big idea in this class. So like, we need to make sure that our programs do the right thing. In terms of peanut butter and jelly, it's like, we need to go and eat the sandwich and make sure it tastes right. As far as programs go, we need to run our programs and make sure they do the right thing. So we need to learn how to test them. There's also going to be assumptions that come up all the time. So like, when I give you a problem, you might notice that there's some things that I don't mention in the problem statement, but you still need it in the solution. Like, it's just some stuff that's not talked about. All right, so those are the assumptions involved within the problem statement. So you're gonna have to learn to pick those out, even if they're not there. Here's a silly example of like assumptions. Like, if you want to go and light a birthday candle on your birthday, then you can't go and sue the manufacturer for trying to light it underwater, right? Because the assumption is that you're never going to do that. You can't light a candle underwater. Okay, so similar things happen with programs. And yeah, the final thing is computational thinking, which I kind of explained on the last slide. That's just by where you think sequentially in a certain order, you think clearly and at the right level of abstraction. So low enough that the computer can understand. And I'm going to put a nice rainbow star next to this one because this is the goal of the class. If I get you to do that, everything else is easy. All right, it'll take some practice though. So yeah, that's where we're going. And I guess now let's get started with just like pieces of a computer, just in case you haven't heard of these before, just to make sure we're all on the same page. This is just a quick high-level overview of what a computer is all about, right? So you can think of it as a bunch of different pieces talking to each other. So input devices are very important in a computer, right? Those are ways to give information to the computer. So for example, your keyboard, you type on the keyboard, you're giving information to the computer. Your mouse and your touchscreen are other ways of like giving information into a computer, right? Telling it what you want. There's also the opposite, right? Output devices. To see stuff, to get stuff out of the computer, you can put it on a display. You can project it. You can print it onto paper, right? So that's an output device. So that's the duality there between input and output devices. And then the bulk of the work of your computer is happening on the processor, or the CPU. That stands for Central Processing Unit, right? That's like the brain of the computer, and that's running your program. So another word for run is execute. So it doesn't mean like you're killing your program, that's just another silly synonym for running your program. So processor, or the CPU, is a very important place that we care about understanding in this class. And then also, as your program is running, it's interacting, it's got to save information for later in a special place called the main memory. So the main memory and the processor, they go hand in hand. So that the memory is where, also called RAM, by the way, random access memory. That's storing information about your program as it's running, all right? So every program, when you double click it to run it on your computer, it's getting copied into main memory so that it can run on the CPU. Like, that's the only way to talk to the CPU, is to get it into the main memory first, right? So you can't go like straight from the hard drive into the processor or something. It's got to go through the main memory. And so that's why if you want to run a bunch of programs at once, you need a bunch of RAM. You need more RAM to run more programs, right? That's super fast to access, much faster than like a hard drive or a SSD. And then secondary memory is the other stuff. All right, so main memory is populated when the computer is turned on. Secondary memory is like your hard drives, your flash drives, your solid state drives. Those hold a bunch of stuff, like on the order of terabytes rather than gigabytes, where you have RAM. Holds a bunch of stuff, but super slow to access. And so that's why I want to copy it into main memory as it's running. But it's also useful in when the power goes out, right? So secondary memory is where you're saving your programs on when your power is off for your computer. So those are just some simple parts of a computer in case you've never heard of them before. And now let's get into C++. So this is a programming language that we're going to learn in this class, and it's been around for a while. It's older than me. It was invented by a wonderful Danish man by the name of Bjarne Stroustrup. I think that's how you pronounce his name. So here he is, the legend. It's based on an earlier language called C. So there's like a joke going on, and you might get to. I think I might show you the butt of the joke by the end of this class. So it's based on a language called C, but there's some pluses now. So it's C++, and here's what it is. It is a high-level language, first of all, and so that means it's good for us, right? It looks more like English than ones and zeros. So I've shown you a little bit of a program already. It looks a little bit like English. It's not me typing binary ones and zeros all day long. All right, it's me typing something that looks like English. Look, that's my program. Not quite the blah blah blah, but like you get the idea. It looks a lot like English. It's high level. That's what we say. And then it's also what's called a compiled language. So to run this program, you can't just like give this to the CPU. You can't give your big long essay to the CPU. You have to compile it. All right, so you have to give it to something called a compiler. That's a separate program. So the compiler takes your program. It's like a little box. You give it your program file that looks like English, and then it converts it to the binary form, to the ones and zeros that your computer understands, because that's how CPUs think, right? They think in terms of high voltage and low voltage, ones and zeros. All right. So that's the job of the compiler, to translate your high-level language to what's called machine code. All right. So let me write for you the first C++ program that I kind of want you to understand. All right. This is the simplest possible C++ program that I'm about to write for you. It's one that does nothing at all. All right. That's the simplest program, one that does nothing at all. So let me go back out here. I'm going to make a brand new program file called do nothing.cpp. .cpp is the standard extension for C++ programs. And here is a program that does nothing. It's like the simplest program that you can write in C++. I have to say the following: int main parentheses curly braces and then return 0 semicolon. I will explain what all this means in just a second, but that is the simplest possible program. It does nothing at all. All right. And so let's see here. I'm going to compile it through the compiler that's called G++ in this class. I'm going to give it the name of the file. Sorry, not welcome. It's do nothing. Excuse me. And then if I hit enter, what it does is it's going to make for me, here's my original program, it just made for me this file called a.out. Let me get rid of that and show it to you again. So it's just do nothing, there is no a.out. If I say G++, give the name of the program, it makes this brand new thing called a.out that I will run with /a.out on the terminal. And I hit enter, and it just gives me a brand new terminal prompt because it did nothing. It ran the program ended, nothing's happened, all right? So that's a lot of new stuff, I know. But that's the simplest program. And so I'm going to explain that in a second. But before that, though, I want to get to just the terminal in general. Because down here, and up here technically, before I started editing the file, I'm in this magical place called the terminal. All right. And so you can give it little commands. It's a text-based way to interact with a computer. And this is pretty much what it's going to look like. Now let me do it. All right. So like when you get let's see, how do I want to say this? When you log in to the class server, for example, it'll be on the terminal, and it will plop you into a place called your home folder, which is signified with this tilde. All right, that's your home folder. Let's see here. I guess I do want to do it this way. So yeah, this is what it's going to look like more for you. You still see the tilde, but it looks slightly different. So when you log in on the class server, this is exactly what it's going to look like for you. It's going to say like your username at the class server, and then tilde for home folder. And so that's shorthand for your home folder. You can see where you are based on the prompt. And if you want to see the files in your current directory, there's always a concept of where am I right now. So it's like, what folder am I working in? It's your home directory by default. ls shows you what's there. All right. So here, ls stands for list. List all the files in my current directory. So if I'm in my home folder, it shows me all the files there. All right. pwd is also going to show you the full path for your current directory. What is this terminal looking at right now? What folder is it in right now? pwd. So here is the folder name. It's slash is the root directory. There's a folder called home, and then there's a folder with my username inside of the home directory. So that's the home folder, all right? So that's what your current working directory is. And then if I want to go and work inside of another folder, like code from class, that's where I was, I kind of want to like double click it essentially. You have to use a command to get there and move inside of this folder. That's called CD for change directories, all right? CD, and then you give the name of the folder you'd like to go and work inside of and have that be your directory, all right? Your current working directory. So, all right, code from class is somewhere I can go right now. So CD code from class, hit enter. Do you see how my prompt has changed? PWD tells me that I'm inside the code from class folder, inside the lot folder, inside the home folder, inside the root directory. And then also ls shows new stuff. All right, so sorry it's a little hard to read, but there's our CSCI 40 online folder that I can go see CD inside of. Hit enter. PWD, see it's changed again. The prompt is also telling me that it's changed. Bam, ls, there was a lecture 1 folder inside of that. CD, lecture 1. ls is that's where I was. All right, so that's where the program was, /a.out. I can run it again. Beautiful. So that's that. If you want to move around quickly without having to remember folder names, you can say cd ... to go back out to where you were. So like I am working inside the lecture 1 folder right now. If I just want to go back to the CSCI 40 folder, that's the parent directory right now. If I want to go to just this one, I can say cd ... That gets me out 1. So you see where I am now? See how I went out 1? So now I can see all the lecture folders. There's just the one right now. So that's shorthand. The ... is shorthand for your parents directory. And then the single dot is a shorthand for your current directory. So that's why when I say ./a.out, it's like run the thing in my current directory, but I'm in the wrong folder right now. All right. So then once you're in the right place, you have a program file, and you're ready to compile it, you say G++. That's the name of the compiler. That's short for the GNU C++ compiler. That's what we're using in this class. And then you give it the name of the program. So that file needs to exist in your current directory. And so you say G++, name of the program, do nothing, for example, hit enter, and it will update if you had changed it. It will update this a.out file. That's the default name of a program, all right? Which you can then go and run with the /a.out to run your program. There we go. So it's like in the current directory, run this thing, all right? And then it ran it and it did nothing. If you're ever lost, you can always go straight to your home directory by saying cd ~, all right? And then from there you can be like, all right, cd, you can go in one fell swoop to wherever you want to go. Cd code from class /CSCI 40, oh gosh, CSCI 40 online lecture 1. Like you can go straight there if you need to. Like there's a way to do that, but you can do it one by one if you'd like as well. All right, so that's how you run the program, and then the / stands for run the thing in my current directory. Just like double dot is your parent directory, single dot is your current directory. So I guess there it is running the program. If I said cd dot, it really does nothing. So it's just dot means stay here. That's your current directory. It's shorthand for that. All right. So this is a slide you're going to keep coming back to. So you know it's slide 36 apparently. All right. So there's that. The next thing that I want to show you is how to write your code. All right. So in order to make a .cpp file, you have to make a brand new file and type into it. All right, so that's called using an editor. All right, so an editor edits a file. So there's a bunch of different ones of that, bunch of different kinds of editors, which are just programs that you use to edit files, and they can be in the terminal, like I was showing here, or they could be graphical, like technically Microsoft Word and Google Docs. Those are examples of graphical editors, right? So there's a bunch of different ones to learn, but I would say that the first one that I want you to get good at is using Nano. All right, the one that I've been using in class is called Vim. I want you to get good at that eventually, but as you start out, I would say use Nano first. All right, so terminal-based editors are just new commands. So you say Nano, that's the name of the editor, space, the name of the file you would like to edit. All right, so you say Nano file name, and hit enter. It plops you into that file. So do nothing, for example. Hit enter. It's now plopped me into this place called Nano, and I can move around with the arrow keys. The mouse doesn't work in the terminal here. It does in Vim though. And then you can start typing. Like you can change stuff. Blah 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 blah. And then once you've made your changes, you can save and quit with the Control X command. So this caret character means control. So it's like if you were to type Control G right now, it's kind of telling you how to use Nano. It would give you help about Nano. If you were to do Control X right now, it would exit out of the program, exit out of this file, and save it if you wanted to. So I hit Control X just now. It's like, do you want to save this? Yes or no? So I'll say Y for yes. What file do you want to call this? Do you want to call it the same thing? And I'll just say Enter for like, yeah, keep this same file and overwrite it. Still keep it called do nothing. And so that's me changing the file. There it is. I can go back into it with Nano, and it has that new line. Like I can save it again, add a new line, get back to it. Like that's how you edit a file. Okay. I like to use Vim instead. It works just like Nano, but you have to do the Vim tutorial in order to do it. So do not try to say Vim file name just yet. It works the same once you learn it, but the meme is nobody knows how to quit out of Vim, and so do not try it yet. Try Nano first, and then do the Vim tutorial. Do the Vim tutorial so you can get good at Vim, and that one lets you use like the mouse and stuff. So that's pretty cool. There are other editors that people like. So that like Visual Studio Code, that's a big one. It's a big name these days. That's a graphical editor. I can help you set that up if you'd like to get that working on your home computer. But I do want you to get good at Nano and Vim eventually. All right. So yeah, that's how you edit code. You have to use an editor, and yeah, before I like explain C++ to you in detail, let me try to motivate, like, why are we learning this language in this class? Okay, so there are other languages that we could learn right now. So here's kind of the motivation for why I'm required to teach this to you. So though it is a high-level language, so it looks kind of like English compared to ones and zeros, it is on the lower side of the higher level languages, if that makes any sense at all. So it's a little bit closer to the bare metal. So you're able to ask the computer to do more complicated things because of that, and like it doesn't hold your hand as much. So that's really good for your first language, because that means you're going to learn the right strategies, and you're not going to make any silly mistakes because of that. You're going to learn how to talk to the computer at the right level. All right. So you'll get closer to the bare metal that way. It's also very fast. So yeah, pretty much any program written these days that has a care about speed, so like Adobe products, the back end of any web browser these days, pretty much every game engine in any video game, everybody's using C++, because it like gives you a nice combination of like high level, looks like English, but also you can talk to the bare metal CPU and tell it exactly what you want. So that's a good reason to learn it. And then also just like, it's what all the other schools are doing too. So like, it's either this one or Python, honestly, if you've heard of the language called Python. So Fresno State, for example, they do C++ first, and so that's kind of why we do it. But it's a very common language to learn first. All right. So yeah, let's get into like the process of compilation now. So I told you that C++ is a compiled language. I showed you this G++ thing. That's the compiler. It spits out a file called a.out, unless you tell it to spit out a different named file. But let's talk about the process of compilation. All right. So I will show you this slide again, and you will know more by then. But like, I just want to show it to you once right now. So here is what a compiler is all about. So you've written a program. Here's your do nothing.cpp file. The job of a compiler, here's the compiler. It's called G++. It translates your single program file, your 1.cpp file, into the ones and zeros that eventually can be run on your CPU. So it translates it into something called machine code or object code. That is ones and zeros that represent your program, essentially. All right, so that's this. And that's called object code, and it's usually with a .o at the end of it. What is confusing about G++ is that it does two things. It both compiles your program, makes the object code, and then it also links it. And that's what produces the a.out. So I'm very sorry. It's a little confusing to start out, but I will come back to this slide. I'm not forcing you to memorize it or anything right now. I just want you to have heard these words by the time I come back. All right. So yeah, it spits out object code, which is ones and zeros for your one file, but usually your program doesn't exist in a vacuum. You like to use other people's programs. Maybe you've written another .cpp file that you want to include in your current program. Like you want to use the stuff that you wrote there, or you want to use other stuff that people have made before. Like if you want to print to the screen, you include something called a library. A library, that's a cute little analogy, right? It's a fun metaphor. It's like you go to the library and you check out a book that somebody's already written for you. So libraries and programming are pre-implemented pieces of code that just help you. So if you want to print something to the terminal screen, you'd include a library called IOStream, and I'll show you that in a second. And inside of that, there's something called standard : cout, and that gets you your terminal screen. your terminal screen. And like you want that functionality in your program, so you want to link your program with that. And so G++ does that by default, all right? So it's a little confusing that the compiler and the linker is both G++. It's doing it all for you, but like I want you to understand that it's a two-stage process secretly, and by the end of both of them, after you've compiled and linked with other stuff, then you finally have a program that you can run. You have your a.out. That's your final executable program with your / that you can go and run, all right? Just the compiler, it's not ready to be run yet. It's ones and zeros, but it's not ready to be run because it needs to be linked, okay? So that, in a nutshell, is the compilation and linking process. And now that you've seen all these things, all these terminal commands, you know what an editor is, you understand kind of at a high level what the compilation process does, we're ready to write some real programs that do real stuff, all right? So let's do it. Are you ready? So the very first program that I want to write and actually explain is going to be a program that prints out to the screen Hello World. It's the Hello World program, and this is just a customary thing. They would take my computer science card away if I didn't do this for you first. Just like the first thing you're supposed to write when you learn a new language is a program that prints Hello World to the screen to just prove to you and to the computer that like you are the master of this language or something. Okay, so that's the idea. And so let me make a program that prints Hello World to the screen after you compile and run it, and then I'll explain everything. All right, so let me take this back to normal first of all, and then I'll make a brand new program called hello.cpp. All right, and so I'm going to start typing right now, and I will explain everything that I type in just a second. All right, I just want to get the program first working and running, and then I'll explain everything. So include iostream. Let's see, I don't want to do that yet. Int main, parentheses, curly braces, you remember that from the do nothing program. I still need the return 0, that's all got to be there. And then here's what's going to print for me. I'm going to say standard : cout, give some arrows, and then between quotes I'll say hello world, and then a semicolon. All right, so that is going to be my program. And let's see here. I think that's how I want to start. All right, so I'm going to compile this, so I've saved it. I've got my hello.cpp now. I'm going to compile it, G++, hello.cpp, hit enter. It's overwritten the a.out file. So if I run it now, /a.out, it prints hello world to the screen. Isn't that beautiful? It's lovely. So it looks a little funky because it's got the terminal prompt on the same line. So we'll fix that in a second, but like it worked. You ran it, it printed something. Bam, run it again, it prints hello world to the screen. Isn't that beautiful? So cool. All right, so let's talk about things. So I would like to mark up the program and show you what's going on. All right, so I would like to write some comments inside of the program. So there are two ways to make a comment in your program. It's // makes a single line comment, and then these two guys make multi-line comments. And a comment is just a place for you, the programmer, to write notes for yourself. It's not part of the program. So this is very useful for me in this class, right? So if I put 2 slashes and start typing, this is a single line comment. All right, it's called a comment. It's meant for programmers only. It's not actual code. All right, it's not code. And this is a single line comment, so it's like you have to put 2 slashes at the start of every comment line. All right, if you want to type a bunch of lines that are comments, you do the // and like this is a multi-line comment. So have as many lines of comments as you need, and then end it with a //. So that's helpful sometimes. And so now I can mark up this program with comments, and it doesn't change the actual code. All right, so include iostream. That's the first thing I want to say. That's a library. And this gives us, by using this gives us access to standard : cout. That's where it lives. So now it knows about it once I say this. Include that library, please, so that I can use it. And then here's the main function, right? This thing between curly braces, it's called the main function. This is called the main function. It's where the program starts. It runs all the lines of code in this main function. All right, so standard : cout, that's the first thing it does. It runs this line of code, and lines of code are specified. They're written in between semicolons. So like semicolons are the periods of C++. It's like I'm done with this thought. Return 0 is another thought. It's another statement in C++. Right? So standard : cout is the terminal screen. All right, and then things between these quotes, those are things that we can print and give to cout and give to the terminal screen. They're called strings. It's a new term. You can think of it like strings of letters on a friendship bracelet or something. So we call everything between quotes in programming a string. All right, it's like a string of letters. So that's that. And so that's a line that once that runs, it'll print hello world to the screen. And then this return line has to be at the end of every main function. This marks the end of the program, right? It's like, I'm ready to give up. I'm ready to return. It tells the terminal, and also this 0, it means something. It tells the terminal, the person who ran the program, right? You're having the terminal run your program. It tells the terminal that your program executed successfully. All right, that's what the 0 means. Any number other than 0 is like a number that indicates failure, but 0 means success. So like if we could hear when we run this line, our program ended successfully. So that's a C++ program in a nutshell. All right. So yeah. Also the semicolon. Semicolon marks the end of a C++ statement. Right. That's just a single line. It's like a single thought. It's the period. Right. It's the equivalent of the English period. It's like, now I'm done. So yeah, that's our first program, and let's make it cooler, all right? So I don't like that this line, like it's printing out and then it's giving me the terminal prompt on the same line. I don't like that. So I would like it to print hello world and then kind of press enter so that this is on a brand new line. That's what I want, right? Because ls kind of does that. Everything else does that. Let's do that ourselves. So here's how you do it. Here's how you say press enter please for me. You say \n. All right, and this is called an escape character. So it's not actually going to print to the screen \n. This stands for something else. It's going to print enter. It's going to type the enter key for our keyboard. All right. So these are called escape characters. And let's see. Dun, dun, dun. \n is an escape character, and that means it's going to get replaced with something else. So this \n means new line. So it's going to press enter. \t makes a tab. \r does something cool. I encourage you to try it. And that also means, though, you can't print a \, like this because it's kind of waiting for something else. It's supposed to wait for something special. So if you want to type a single \, you have to escape it, we say, and put 2. 2 becomes 1. All right, but I'll use this for a new line. And so now it's going to print hello world and then also press enter. I'm going to recompile it, rerun it, and look at how it types it and then presses enter and gives me a new prompt on the next line. That is beautiful. That is nice. All right, I love it. So yeah, that's pretty cool. Another shorthand for this, I swear, even though it's longer to type, this is useful sometimes. Instead of \n, in the IOStream library, there's also something called standard endl, which stands for end the line. So you can give to cout a bunch of stuff. You just got to separate it between these arrows. You can give standard endl, and that's also the \n. That's also end the line. So it's like give this text, give this string, as well as press enter, essentially, and it does the same thing. All right. So I think that's what I wanted to say there. And yeah, then one last thing is, wouldn't it be nice if we didn't have to say standard : all over the place? This just means it's from the standard library. All right. It'd be nice if we could skip that and just say cout, just say endl. And we can do that by saying using namespace standard at the start of our program. So after this, after I've included the library, I can say using namespace standard semicolon. This line is special. It's the one that doesn't need a semicolon, but every other line is like real C++. This needs a semicolon too. This says, this uses the standard namespace, we say. So now I can skip the standard : and I don't have to say standard : cout. I can just say cout. I can just say endl. This is a little bit simpler, less typing. So I recompile, rerun, same thing. All right. Every time you change the program, you have to recompile it because this is the machine code. This is the thing that's runnable. All right. So I think that's what I wanted to show you there. Yeah. So that's our first program. Hopefully it makes enough sense. So let's have another program that shows like some math. It's like the whole point of a computer back in the day, right? They were invented to do math for us quickly. So let me show you some math in C++. Let's calculate the area of a circle with radius 5. All right. So how do I want to do that? I want to make a new file. Let's call it maybe area.cpp. So I'll make a new file called area.cpp. and I'll fill it in with all this stuff. Like I want to be able to print stuff, so I'll include IOStream. I'll use namespace standards, so I don't have to say standard : all over the place. And that's int main, parentheses, curly braces, return 0. I promise you'll get good at this. You'll memorize it eventually. You'll just be forced to do it so much. And then now, instead of printing hello world, let's print the area of a circle with radius 5. So that's pi r squared, right? So pi 5 squared. So that's 3.14. It's a star in C++ to do multiplication times 5 squared. Let's just multiply by 5 twice. And this is one of the reasons why endl is shorthand, and it's sometimes useful, because now I can say and a new line after that without having to press shift and do \n, because it wasn't part of a string already. So it's like do the math, print out the answer, and then new line. So endl is useful, even though it's more typing than \n. So I'll compile that, area.cpp /a.out, and apparently the area is 78.5. Cool. Isn't that beautiful? Yeah, I think the last part of this that I want to show you is white space. So C++ doesn't really care about the spaces that you put between your lines and stuff, so it's like it really does not mind. It's like this entire line could have been like, as long as you separate with at least one space, like I can tab over, I can do disgusting stuff like this, right? I can do, as long as I keep the consistency. So like my program could look like this. Sorry, it keeps putting stars for no good reason. There. Like this is the program, and it still works. C++ does not care. But this is disgusting to look at, right? Also, alternatively, go back to normal. Alternatively, this could have been the program. Like it could all be on like one giant line. That also works. C++ does not care. But please, for the sake of yourself, reading the program again later, be sensible. Like write it pretty. Try to follow my style. So yeah, I think that's what I wanted to say. So yeah, we wrote a few programs, we compiled them, we ran them, and I think you understood some of that, didn't you? So nice. Please pat yourself on the back right now, because you just wrote some programs and you understood them a little bit. All right, you could do this. You're very cool. All right, I don't have much to show you left today. I just want to show you a few more examples so that I don't melt your brain too much. But you're coming pretty far in one lecture. All right. So to do anything useful now, we have to make variables. So let's talk about those. So a variable is just a box in memory. It's giving a name for something else. All right. So this line. All right, what this line does in C++ is it makes a brand new variable called x, and it holds 42. So it essentially makes a box in memory, calls it x, and it places 42 inside, so that now I can just say x instead of saying 42 all day long. So it's nice, and it helps us abstract over stuff. Right? That's what a variable is all about. It's similar to math. And then this int means that x holds an integer value. That's what 42 is. It's a whole number. It's an integer. All right. So there's different types that your variable could hold, and you have to stick to the type that you say you're going to put in it. All right. So I like to think of types as like clouds. Like what could go in this thing? So the int type, what could be an int? It's nothing but whole numbers. All right. So like 42, 8, 0. These are whole numbers. Negative numbers count. Negative 42. These are whole numbers. Those are integers. So they can go in int variables. All right. If you needed decimal places, you have to use a different kind of variable. It's a different type. It's called a double. All right. So the double cloud is a bit bigger than the int cloud because it kind of contains ints, doesn't it? So doubles, like you can hold 3.14. That's a double. All right. It's a double value. You could still hold whole numbers, but it's kind of like there's a implicit or explicit 0.0. All right. So it's a little bit more precise. So that's double. There are other types too, though. If you want to hold a single character, that's the char type. Some people pronounce this as char, but I pronounce it as char. So you can hold single characters in the char type, and instead of using double quotes to specify a char, you use single quotes. So it's like that kind of reminds you can only put one thing in here. So like you can hold the a character, you can hold the space character, pretend that's a space. And then string, that's another type that we know, right? So a string is a type. That's an actual name for something, even though we haven't said it yet. We've just used it. A string is stuff between double quotes, all right? So like, hello, that's a string, all right? Capital the, that's a string. You can have spaces. You have a big long sentence, right, as a string. Notice that you could have 300 as a string, and it is not the number 300, is it? Woohoo. There's a big difference between this and like the int 300. So keep that in mind. I'll show you the difference later. But like those are some types, and so let me show you those. All right. I'll make some variables that hold different types, and then we'll print out the stuff they hold. So I'll make a new file called vars.cpp, and I'll get my standard boilerplate code that you know and love now, and let me make it a variable called x that holds 42. All right, so this makes the box. There it is, right there. It lives in memory now. And then what do I want to do with it? Let's just print out its value. So here I am printing x, and then a new line right after. All right. So this should print 42. So g++ vars ./a.out. Bam, 42. Beautiful, right? And let's do the same for the other types. Let's be like, all right, let's make a double, call it d, and have it hold 3.14. And so now if I were to print d, recompile, rerun, now I got my 3.14. So that's the type name. That's the kind of thing that can hold a number with decimals, is a double. And let's do the same for chars and strings. So char, call it C, holds a single character between single quotes, like capital C for CSCI. And then strings are very similar. So string, the string type though is actually not baked into the language. String s equals double quote something, so like hello, and then print s. The string type does not live by default in C++. You have to include it. It's part of a library. So you have to include the string library to use string variables, to use the name string. All right? So that type, you must include the library to use it as a variable, to have that name there. So you have to include the string library to use the string type. You did not have to include the library to use a string as you're printing it. Where was that? That was in hello. Like, this is still a string. I just never put it somewhere. If you want to put it somewhere, that gives you access to the type string once you include the library. All right. So yeah, this works as you would expect. So those are different kinds of types and different variables that hold those things. And now I can say s instead of hello all day long. Let's see here. All these programs that I've written so far are kind of boring because I'm like hard coding what's going on. Like x is 42. It's going to be 42. I have decided that. To make your programs cool, you can make them interactive. So the opposite of cout is cin, right? And that gives you input from the user who's running your program. And you can place the answer that they give you, like whatever they type, into a variable with the cin statement. So let me show that to you. So I'll make a new file called cin.cpp. And remember, you're going to get all these files. So let's see here. Let's say I would like to make I'd like to get a number from the user, let's say. Like maybe we can do math with it. It's like this is a more interesting interactive program now. So I'd like to get a number from the user with the cin statement, like cout, hey user, enter a number. It's nice to give them a little prompt and like a space. And then I'm not going to break the line. And I'm going to say cin. By the way, this arrow, these arrows are placed like this because you're giving information to cout, right? You're shoving text into the terminal screen. Cin is the user's keyboard, and I want to put that. I want to put whatever the user gives me into like a variable called x. So which way should the arrows go? Which way is information flowing? It's from the keyword to the variable. All right, so that's going to fill up the variable. All right, and that's going to ask the user to type. So the variable needs to exist first, though. So I have to create this variable. So there's no use saying like int x equals 42 because this is going to change it immediately. So instead of saying equals something, I can just say int x semicolon. All right, and so x right now holds question mark. It holds nothing. And this is fine as long as it eventually holds something. All right, it holds nothing right now. I'll be more precise with that word later, but I'll fill it with whatever the user types. So I just had to say that x needs to exist. So like, please memory, make something called x that holds an int, and now I can ask the user for that int. Read it in from their keyboard, all right? So this will be fun to look at. And then let's just spit it out back to them. Let's be like, hey, you typed, and then like space x and a new line. And then we can do math with it later. But let me just show that to you. So watch how the program runs. It makes the variable, holds nothing. It prints out this, internet colon space, and then it doesn't break the line because cin waits. See how that's a nice clean prompt with that space and on the same line? So it's going to wait now for the user to type, and they're going to hit enter. So there's 42, you'll hit enter. That's going to take whatever I typed and shove it into X. And then it's going to let us use that, whatever the user gave me. So if I rerun this and type a new number, it's a different kind of program, right? You can have it do different things. That's pretty useful. All right, so that's getting information from the user. You can use cin to get stuff into a variable that you've already made. Okay, so you can do the same for other kinds of types. Like, hey user, give me a char, give me a double. So just gotta have it exist first, and just be like, all right, enter a char, and just be like cin into that C variable. Do the same for different things. Be like, do it for a double. Make space for it in memory. Ask the user super nicely with a prompt. Enter a double, and then we'll read into it. All right. And so notice I'm not ever really breaking the line. It's the user who's typing enter. So that breaks the line for us, kind of. So, and then I can, of course, print them out. So I'll print out like C and D, maybe down here. See out C and a new line, print out D and a new line. So here's like the relevant code. Recompile, rerun. So enter an int, I don't know, 100. Enter a character A, capital A. Enter a double 3114. And so here it is, it's saved them all, right? It's showed me the number that I typed, and it's showing me the character and the double that I typed as well. So I have access to them. I can do math with them if I wanted to. Like C out D times 2 or something, D squared if you wanted to. So yeah, those are variables and types of variables, as well as getting input from the user. All right, so we've just learned a bunch of cool new stuff. Let's see here. And so let's stop. I now have exercises for you to try. So please pause the video, try these out yourself, and I'll show you the answer once you give them a try, though. But let's just make sure you're remembering stuff. So what does a compiler do? Which of these is it going to do? If only it made you a peanut butter and jelly sandwich, right? But which of these is it going to do? What's its job? So the job of a compiler is to take your high-level language program and make machine code out of it. Make ones and zeros. All right? So it's going to do the translation. That's the process. All right? So running is just the job of the terminal. Storing your program is like the editor, saving stuff for you. But C is the answer. That's what a compiler does. Translates your program into machine code. All right? And then now, all right, let's say that I've made a file. I've made a new program called x.cpp. How do you compile it? What's the terminal command? Do you remember? And then how do you run it? What's the terminal command for that? So it's this slide that you're going to want to go and look back to, right? But it's G++, right? Name of your program, x.cpp, to compile it, and that generates an a.out file that you can then go and run with the /a.out. All right? There we go. So the last thing that I want to show you today, before we talk about lab stuff, so there will be, I guess, 3 different main videos for today, because I do want to have like a little lab section for you, so we can get you on the class server and everything. So I have made a fun little karaoke demo for us, just another example of like how the kinds of stuff that you will learn in this class. So it's another example that I don't expect you to understand yet, but you can understand most of it. All right, so what we're going to do is we're going to have the computer sing Frozen's Let It Go to us, of course. So I cannot play this for you and record it because sadly YouTube will take away my account, but you try it yourself. You'll press play when this program's running, and it will legitimately sing this, sing out the text of the song to you. But here is a file. I've made it. It's called karaoke.cpp, and what it does is it does a few things, right? It's mostly outputting things to the screen because it's going to sing to you, right? The snow goes white on the mountain tonight and all that. But in addition to that, there's one other thing. This is called a function. It's the pause function, just like this is the main function. So I've made a pause function. Don't worry, I had to look up on the internet how to do this. But what you give to it is the number of seconds you want the program to stop for. All right. So all this program is, it's just a bunch of printing and then having the program wait for a few seconds so that it lines up with the actual song. And so you can understand this, right? Even if you don't know how this pause function is written, you can run these lines, right? It's like this is going to print that and it's going to wait a second. It's going to print that and it's going to wait a second. And then apparently it's 20.25 seconds until the first line of the song. All right, so go to this YouTube video, press play right as the program is telling you to press play. So let me compile it, g++ karaoke.cpp. And then if you don't want this to be called e.out, you can say -o. All right, so I'll say g++ karaoke.cpp -o, and then I'll just call it like karaoke without any extension. And so instead of overriding it.out, it has made a file just called karaoke that I can run. All right, so that's what the -o does for you. I will not test you on this program again, just like the first one. This is just to show you what you can do. You can understand it though. So like you hit enter, it's running, press play in 3, 2, so you'll be at the video, and then you'll press play right now. And then apparently, like what I did is I took apart the subtitles file for this video. And so if you were playing it right now, like you got the piano going right now, and then it's going to wait 20.25 seconds, and it's going to start singing to you exactly as the program should be going. So then like it's singing. Okay, so try it out yourself. It's much cooler that way, but sadly they will take my account away if I were to show this to you. But it's legitimately singing to you in the right order at the right times. Please try this out yourself, and you could understand this program, right? Even if you didn't know how to write this pause thing, if somebody gave that to you, it's like, all right, all it means is stop the program for a certain amount of time. Like, all right, go. Pause for a little while. Print out this lyric. Pause for a little while. All right, and that's pretty much the program, all the way down to the return 0. So you can understand this. If you wanted to stop early, you can press Control-C to end the program. But I highly encourage you to try this yourself and have the terminal sing to you. All right. So I'll give you all this code to try out yourself, but I think that's where I want to stop the lecture part of today. So there's one last thing to do. Every lecture there's either a lab, like a programming assignment out, or there's like something that I'm going to release. So this first day, I'm not going to release a programming assignment, but we're going to have like a little lab time. And so I'm going to record one more video of what would happen during the lab time, where I'm going to get you on the class server and running a program, like and editing it and compiling it and running it. All right, all that fun stuff. So one last video for the day, and I will see you there.